to get the class recordings up from last time. I still haven't even gotten the one that's after this yet. Sometimes there's technical problems. It's weird. YouTube is weird with uploading stuff. Sometimes I let stuff sit forever, and even by the end of the day, it's still at 50%. It's just hanging, so I have to restart the whole thing. So it took a while to get that up. Also, by request, Evan came by and asked, hey, you said you had an integral table that you could hook us up with. So in the content area of our class is probably one of the greatest math references ever produced. So look under Dank math reference or something like that. It's from this calc book, Stewart, that I took calc from. But it's incredible. It's not just integrals and derivatives. It's literally just about anything you'll probably need in your scientific career here at Regis, or mathematical career. Lots of great reference stuff in there. Might want to print a copy, just have it around if you like that kind of thing. Homework, I have extended the current homeworks through Sunday. Seemed like most everybody was done with the preliminary one, so that's great, and making good progress on the second one. So this one is a written homework, because you can't really do what this is about in web work. And we're gonna do this today. You should be able to just really rock on all this stuff. So look in section 138 in the online text, whatever version you have of that. And for 1 and 2, I'm gonna ask you to use technology. I'll show you some technology. In fact, I have it linked to in our world class page. You're free to use other technology. Our book really likes Sage, which is an online algebraic manipulator. It's a math tool. You can use Sage. I actually prefer this. I think the results you'll get from this are better. But if you want to use Sage, just Google Sage Math and you will find free compilers, online compilers for it. It's a programming language. And if you like that kind of thing, you might be into it. I would like these 6 to please be done by hand. What you might want to do on these is cut and paste. You're going to create some plots. You could just do a screenshot or snip, use the snipping tool, which I really like in Windows 11. I don't know what you do on Macs. You figure that out. You could just cut and paste the picture you create into a Word doc, and either email me that Word doc with problems 1 and 2, or print them, your choice. Just by the start of class next Wednesday. That's all I ask. And yeah, I think that's all the news. Is there anything I can do for you? Any questions? Any questions on homework 1 on web work? I don't want to spend too long, but I'm happy to address any. Okay, email me. The worst time to email me is on Sunday, late in the day. I will probably not get back to you. So that assignment is due on Sunday. I will be in my office from 2 to 3 on Friday if you want to cruise by. You can come by and ask me anything, and I'll be in there to help you. Or you can email me. Sometimes with web work, you're off by just this tiny thing and you just can't get it, but I'm really good at seeing what you did wrong. One of my favorite things is I was a software developer. If you don't know much about me, I was a software developer at IBM before I came here. Living my worst life at IBM, now living my best life here, doing this gig. But I really love debugging. It's kind of like, I don't know, any coders, do you like debugging? No, you don't like it? I don't know, there's something, this is like, especially my own code. I don't want to debug somebody else's code, but I always enjoyed that. Anyway, sounds like you got no questions, so let's get rolling. Very good. So let's do a couple of things. If I gave you this differential equation, so that of course means dx dt, so I'm just rewriting it, equals x, how would you solve that? hope you know the answer, because we've been doing it. Yes,
I
Lou.
would, divide by dx and get it on.
Divide by x, definitely. Yeah, so separate, right?
Yeah.
Separate the variable. We only know one technique. If I ask you, solve this differential equation, you can only do separation at this point. So I could solve this thing by separation. Let's just do that really quickly. Integrate both sides. Undo this, and then eventually get to this solution. C is an arbitrary constant. And we can check that that is truly the solution by simply taking the derivative. So check, what's x dot? Oh my God, it's that, that's easy. And that's actually equal to x. Woohoo, neat, it works. So there's one, we can solve that. But what if I said to you, what does the solution look like without doing this? What does the solution act like for every possible initial condition? So like right here, I haven't used an initial condition, but I know what E looks like, so I can picture these E curves just kind of peeling off. And if C was negative, I could figure these off. But we're going to talk about a way to look at this today and gain holistic understanding of all possible solutions. We're going to talk about qualitative solutions today. Qualitative solutions. And the key to qualitative solution, well, let me actually get more precise, to first order. And you should definitely be reading the book too, because there's certain things like this that I'm not defining, but it is defined in the book. That just means the first derivative is the highest derivative that occurs. That won't always be the case for us down the line. To first order differential equations that look like this. X dot equals a function of t and x. That's an x, something else. Or maybe it's y prime equals f of x, y. So here I have y and x, here I have x and t. And they're the same thing, same rhythm. So how do I get that? I just look at it, how do I understand everything about it in an instant? And to get that solution, we actually have to understand something deeper about what this means. So when we did this, you're just, so far it's been like, here's some symbols, move the symbols around, do calc with the symbols, there's the answer, whatever. But what we want to understand is truly, what does a differential equation mean at the heart? What does it mean geometrically? So we're going to take a geometric approach today, and kind of throughout the semester, interchanging that with symbolic approaches and numerical stuff as well. We're not quite there, but this is going to lead us up to how a computer actually solves a differential equation. So after we talk about what we do today, you could go write code to create solutions, which is pretty cool. So a geometric approach. The key here are direction fields. Direction, or sometimes they're called slope. That word is slope. Sorry, that looks like, I don't know what that looks like. There we go. Slope fields. And let's actually work with this, because I feel like this is probably better on your brain than that is, unless you do a lot of physics and chemistry and stuff like that. So if I have this equation, dy dx equals f of xy, the way we're going to think about this today is that this is the slope of a tangent to a solution at the point xy, and here's the formula for computing that tangent slope. So let me write that out. This is the tangent slope to a solution curve at point xy, and this over here is the formula for computing the slope. And that's it. And once you understand that, you've actually instantly gained a deep understanding of what is going on here. So let's put it to use. Let's actually do this one. So I'm going to actually translate this into the yx version. So let's say I've got dy dx, the first derivative, is equal to the y coordinate. So here's the game we're going to play. We're going to take a plane where our solutions will be plotted. We're going to set up our variables. I'm going to, in some way, try to understand what the tangent slope looks like at every single point in the plane and fill the plane with little lines representing tangent slopes. So let's do a little table just so you have this at your disposal. So if I have x, y, then m, which is embedded deep in your soul as slope, hopefully. Right, I hope, right? Is that right? Am I right about that? Yeah. So slope right here. So at the point 0, 0, what is my tangent slope? Well, it's just the y coordinate. So this is saying the tangent slope is exactly equal to the y coordinate at your point. So it's just 0. What about at the point 1, 0? Well, it's still 0 because it looks like the x coordinate plays no role in the slope. And so here we can just put x 0 and the slope will be 0 for any value of x. Let's do another one. Let's move up. So actually, let's actually fill this in. All along the x-axis, notice that here when y equals 0, I'm on the x-axis. So at 0, 0, the slope is 0. So right at this point, I'm going to put a little arrow indicating flow straight across 0 slope. And what we're going to get is a table of flow in the plane. You can kind of think of this like an air hockey table. Do people still play air hockey anywhere? I don't know, think of it, okay, just like a body of water. I gotta stop like old people stuff. But like a body of water, and at every point you put a leaf onto the pond and you watch where it flows because there's vectors directing that leaf all over. And that's what we're doing here. We're looking at the current in the plane. So then let's move out here to 1, 0. At 1, 0, I've got flow. And notice I'm moving from left to right. That's pretty standard, especially if this is time. We think about time moving this way. And then at any point along here, so I'm actually just going to kind of make a bunch of little arrows on the x-axis that say, hey, if you're on the x-axis, your immediate trajectory is directly right, horizontal, no change. And then we move up. Let's go to some other points now. So let's say I'm at 0, 1. So at 0, 1, the slope is 1 because it's just the y coordinate. So now I've got to think, what does 1 look like? It's about like that. And so here I make a little arrow that says head at 45 degrees, right on the pure diagonal. Notice that will be the same no matter what the x coordinate is. If the y coordinate is 1 for this one, the output is 1. So literally all along this line where y equals 1, the slope is 1. Any solution that crosses this line will have a tangent of 1, slope 1 at that crossing. So all along here, I'm just going to put these. And this is what I want for those handwritten ones. Something like this. And it's going to get more complicated. That's okay. We got it. So let's add a few more. As soon as I go to slope to the line y equals 2, same rules are going to apply all along here. So let's make some notes. So here m equals 0, here m equals 1, here m equals 2, because that's the y coordinate. So it's a little steeper. I'm just going to make it look, I'm not trying to be precise. I'm just trying to get a qualitative feel. So if this is 1, then this is steeper than 1. That's it. What about here? What if I did at a half? What is the slope of y equals a half? It's a half, because it's just the y coordinate. So here m equals a half. And I'm going to make that halfway between the diagonal and horizontal. So this is a little lazier. And you know, your mileage may vary on how well this all gets done. I'm trying to make that look a little less steep than a slope of 1. I'm starting to feel the flow, right? Imagine this was a pond. Beautiful pond. We're out in the park. It's green. And spring has come. It's April around here. It's lovely. We're just looking at the water. And I put a leaf, I drop a leaf onto the pond right here. What would its trajectory be? Well, if I drop it right here, it immediately heads off this way. But notice that as soon as I move this way just a little bit, the slope has increased. So as soon as I move to 3/4, the slope is 3/4. When I get to 1, the slope is 1. And as I move each step of the way, things become steeper and steeper. And the velocity is pointing me up more and more. So now I know what solutions look like. By just following these arrows and following the flow and imagining a flow in the plane. And this completely, utterly looks like multiples of c e to the x. Any one of those looks like an e to the x curve, and just some scaled version of it. What happens? Oh, what happens if I start on this line right here? Oh wait. Oh, sorry. I'm sorry. My finger. Let me. Sorry. Yes, you were right for where my finger was pointing. What if I start right there? Stay on the line, yeah, but Cormac, yeah, you're right, I'm gonna go down if I'm underneath that. But if I start right on the x-axis, every single thing is telling me keep moving right. So notice that if I start on this axis, I never leave it. What do you call a solution that never changes as you move forward in time?
Constant?
Constant, beautiful, yeah, absolutely. And then like what's a physics-y or chemistry word? Solutions reach what is time? Equilibrium. So here I have what seems to be an equilibrium solution, a constant solution, right at x equals 0. Let's just make a little note here. Equilibrium solution on the x-axis. Cool. And then let's pick up where Cormac saw me pointing, which was below this axis. Everything down here has a y coordinate that's negative. So let's just go across. There's y equals -1. That was rough approximate. That's pretty bad. My scale's all effed up. There's 2 things I'm trying to do less this semester. Say the word like, because I ended up sounding like a valley girl at the end. Like last semester, I'm doing it right now. I can't stop it. Like, dude, like. So I'm trying to say less likes, and I'm trying to say fuck less. I'm working on it. And I just blew it by telling you that. But all along y equals -1, the slope is -1. So I'm going to put little blah blahs, little arrows pointing at what I am approximating as a -1 slope. At -1/2, I've got a -1/2. That's a -1/2. I've got a -1/2 slope, which is a lazier incline. Green slope. Blue slope. Let's do the black slope. So I move down to y equals -2. And things are twice as steep as that previous line. And eventually your ability to produce differences becomes very challenging by hand. But now I've got this beautiful thing, and I kind of wish I had a different color. Let's see if, hey, that's not bad. So if the leaf starts down here, I want to make sure that when it crosses, wow, that's like almost vertical. That's pretty psychotic. I'll make it a little bit less psychotic. Anytime you cross one of these horizontal bands, that's your tangent slope, whatever arrows you've got there. So like right here, there's my tangent slope. Right here, there's my tangent slope. And that becomes mellower as I get closer to 0. But I can fill this plane with slopes. And I'm just trying to kind of get this, see how shitty that's looking. So I can say shit as much as I want. I'm giving myself that. There we go, like so. And I can go up here, and I've got this. I now understand completely and holistically that equation. I know what anything will do. And let's ask a deeper question about it. This is an equilibrium. Capping incorrectly. That's an equilibrium solution here. We talked about that because if you're on it, you never leave it. But the world isn't perfect. Data isn't perfect. And certainly there's always constant change in our world. So if a leaf is on here, it would just take a slight rippling of the waves to move it either up or down. Here's a heavy idea, and one of the important ones for this class. This is an equilibrium solution, but if I veer off of it to either side, I leave it forever. So notice that if I just leave this and just fall a little bit off, my computer, my simulation is off by 1 billionth in its approximation. All of a sudden I'm here, and oh, now I'm veering that way. Now it's under by 1 billionth, 1 trillionth. Oh, damn, now I'm cruising that way. This is an unstable equilibrium because moving to either side of it, any slight perturbation produces drastic change away from the equilibrium state. And I can model this for you very easily with these pens. So an unstable equilibrium is this equilibrium. Now I'm constantly adjusting. That's not bad, right? Not bad for an old guy. That's an unstable equilibrium because if I try to stop here, surely it will fall. Here is a stable equilibrium. We return to it. Does that make sense? Yeah. So an equilibrium like this versus an equilibrium like this, unstable, stable, we return to it. So let's take a look really quick at an archetype of stable equilibria. And there'll only be one in this guy. But let's look at this equation. We're probably going to be talking about this for a couple of days for sure. So let me give you this one. Could you please, one, make me a direction field. Look at horizontal bands, just like we did before. Get the feel, you don't have to be precise. Get a qualitative feel for all solutions. And then if you get that done quickly, solve it using separation, please. So here we're gonna have X's and T's. We're gonna practice just moving back and forth with great ease. And that gets confusing because we're used to X being the horizontal, but it's not. Not here. Is the lighting okay? Do y'all need more light up here?
Just a bit.
No, I bet you got it.
Ooh, yeah.
Is that good? Let me get everybody back to. There's like apparently 3 settings on this slider: off, middle, and full on. So I go. find a stable equilibrium at x equals 0. And this is now we're just having fun drawing pictures, making slashes.
Would it just be a flat line then, over x makes 0 like
I'm
this?
sorry, how are you getting, so tell me, what's this arrow representing?
I don't think it should be an arrow.
Oh, okay,
I think it should just be like flat lines
Agreed.
across the line.
Yeah, so for example, at, oh, and make this x. See
Oh,
here,
you want it
cause,
like-
yeah, cause this is x and t, so that's dx dt.
Oh, gotcha.
Equals that, does that make sense?
Mhm.
We'll just practice doing that. And that might be what's throwing you off on this, I think, a little bit. So when x equals 1, the slope is -1, so all along this horizontal where x equals 1, -1 slope.
Does that make sense? Yeah, so you're getting a stable equilibrium.
Yeah, exactly.
So I'm doing it wrong.
Yes.
Excellent. So check this out, and this, check out, look at my graph here. This is dx dt, and I did this to be provocative. So x is our dependent variable, t is our independent. And that's gonna mess with your brain, but that's good. Your brain needs messing with differentially.
So x is 0. And t is 0.
So when x is 0, I'm on the t-axis.
Yes.
Here's x equals 1, right? X equals 2. So horizontal lines
Mhm.
are where that slope's gonna be constant.
Yes.
Right, so yeah, so when x is 0 on the t-axis,
Mhm.
I just move straight across to the right, because I have
Yes.
slope of 0.
So that.
There you go. There you go. Yep.
Beautiful. And then when x equals 0 and t equals 1, and the slope is greater than 0.
Got it, yeah, exactly. And probably, just for like brain's sake,
Yeah.
the order of those columns, because I know you were doing x and y to begin with, I would have tx, just, but it's okay, yeah, you already, but you know what I'm saying?
Yeah.
Just like keeping ourselves, giving ourselves a modicum of control.
Yeah, well, looks good.
Oh, wow.
That was gorgeous, Brandon.
Yeah, really nice. These are looking spectacular.
Oh, yes. Very exciting, very beautiful work, folks. Some of you are doing an amazing job differentiating between a slope of 2 and a slope of 3. I've kind of made it all pretty unappealing. Once you get one of these, you want to just make a few solution curves in general. If you have different colored pen, that's probably gonna look a little bit better.
just make sure that when you cross an axis, or not an axis, but a line of constant slope, that represents the tangent slope of the thing you've drawn. And then, if you have time, you can solve this thing. Like a separation. And that all looks legit to us. These all look like e to the negative t things. This is if c is positive, and c is negative. I'm going to make a little note here that might be worth making. So, if initial condition is positive, so for example, you've got x of t naught equals positive, then you're in this upper half plane. If the initial condition x of t0 is negative, you're going to find yourself in this lower part, and then right here, this is if x of t naught equals 0. And there we have a stable equilibrium at x equals 0. So I would write that out, and I would say that we have a stable equilibrium solution at x equals 0. Let me ask you a different question. Can I actually get to the equilibrium? Can I achieve the equilibrium if I don't start on it? So if I start, so I've got two very different answers here. Yes, Grayson, why you tell me yes? You say yes.
Well, because it always goes to it, right? Or
It
just
does.
close to it.
There we go. There we go. And
I was gonna say there's an asymptote at the x, so it
Yeah.
won't quite reach it.
so these two answers together make the perfect answer, right? There is an asymptote. This is really an asymptote. Equilibrium solutions will be asymptotes, horizontal asymptotes. And we can get closer. So you're right, Trayson. I mean, I can get as close to this as I want, but it'll always have this little
Yeah.
bit to it, right? At some point, the computer wouldn't know the difference once I exceed the precision of the machine. It might as well be there, but we're kind of working in a more ethereal realm with the math. So the only way I can actually be at equilibrium is to start at equilibrium. Is there any questions at all on this? I want to make it a little bit wilder. Yeah, Lou.
So like, thinking about like energy, like, and like entropy, you want like, it wants to like go to like the less amount of energy state, but then there are like these fluctuations that like apply here.
Is that a question or a statement?
Kind of a question.
What is the question, though? So
It's like this can be applied to like entropy
Yeah.
in that sense.
Yes. Yeah, absolutely. And you can think of the slope. So when we think about energy, let's think about like potential energy, which is 1/2 the mass times the volume velocity squared. So the velocity here is actually the slope, x dot. So this is literally the velocity. This is the instantaneous velocity of the particle we're modeling. And so you're right that this quantity, that as time moves on, that velocity diminishes. And so entropy, well, I don't want to think about it in terms of entropy, but energy decreases. But yeah.
But then like, because energy can't be created or destroyed, it can't be like no energy, so that's why it doesn't reach the line if it's not no energy. It
Oh,
just
right,
goes-
yeah. Yeah, it can't, yes, it will never achieve zero energy. Yeah, unless it started with none, which I don't even know if that's possible. Yeah. Good, awesome question, cool. Physics questions, yes, thank you. Other questions? All right, groovy. Let's do something a little spicier here. So this equation here is a very special type. Notice that the velocity doesn't depend, or this derivative doesn't depend on time at all. So here, the system is system state. Now, screw that. I'm getting wrong words. Sorry. I'm sorry, physics people. That x dot, just keep it purely mathy, is independent of time. In other words, the independent variable. So it's time independent, and then as we go to Latin, like so many people around here take Latin. Like Lou, what is the Latin version of independent of time? Yeah, I don't know. Autonomous is the word I'm thinking of. I don't even know if that's Latin. Is that Latin even? Autonomous?
In chromatic.
Inchromatic. Ooh, that's beautiful. That's not the word we're going to use, but damn, that's a lovely thought. Autonomous. Auto being free of. Tom. I don't fucking know. Oh,
Say
I
your
just
time.
did it. Oh, I just dropped one. Luckily, it kind of got lost in there. Yes, so this is an autonomous DE differential equation. And you can see that because as time moves, if the state stays constant, the position stays constant, which is x, it is completely independent of time as to where we will go next. That's why all these things look exactly the same as we move through time. We see this pattern repeating over and over again. But let's make this a little more interesting. And let's come back to x and y. And yes, I am switching on purpose. So let's say I've got now that. Is that separable? I won't look while you think about it. In fact, I'm just gonna look right up here. And if your answer is yes, don't say that. Because that is not separable. There's no amount of division or multiplication I can do to that to get the x with the dx and the y with the dy. So this is not separable. So we literally, if someone said to you, solve this, you better have another approach. And we will have another approach next week, not till Wednesday. So the best we can do today is find the direction field. So let's take a note at a slightly different, take a slightly different approach on this. I'm going to do a plane again. I want my direction field. I want a bunch of arrows in here. Let me give you an organized approach. Literally the only place in my life I'm organized is math. Everything else is a shambles, just an utter shambles. Come by my office sometime and visit the shamble shack. Here's my office. So what we want to do is we're going to find places where the slope is constant and see what that says about the relationship between x and y. So the thing I'm looking at right now is we're going to find isoclines. And these are lines of constant slope, or curves of constant slope. Curves where dy dx is constant.
So it's kind of a different, it's actually almost completely backwards from what we just did, where over here, we were picking the x value and finding what the slope was. Now I'm gonna set the slope to certain values and then figure out where that happens. So that's an isocline. And so here I'm gonna put dy dx. And keeping in mind, that's my slope. And then here I'm gonna put the equation where that happens. That's pretty bad grammar. So let's start off the easiest, lowest hanging fruit, 0, 1, -1. Love those numbers, they're sweet numbers. So let's set the slope to 0 and figure out where the tangent slopes are always 0, just horizontal. So I just replace this with 0. So I'm gonna plug that into this part of the equation, replace dy dx with that, and I get equals y minus x. In other words, all along the perfect diagonal in the plane. So here we've got, I'm gonna make a little dotted line. You have multiple kinds of dots, and that's the line y equals x. Any solution curve that crosses this line will have a horizontal tangent slope. So all along here, so I'm gonna put m equals 0 down here. Anytime I cross that, my tangent slope will be 0. Now I'm not getting the magnitude, I could, but I'm not going to. And you always want your arrows pointing right for the most part, for all the parts that we're doing for now. And now let's just figure out a few more. Because this is not enough information to drop a leaf onto the plane and figure out where it's gonna flow. So let's set, the slope is 1. And so I replace dy dx with 1, and I get 1 equals y minus x. So everywhere y minus x is 1, in other words, y equals x plus 1, the tangent slope is 1. Now this is kind of a special line. Actually, it's the only one like this in the whole thing. So let's do y equals x plus 1, so there's 1. And notice that it's still slope 1. So it's parallel to this previous line. That's y equals x plus 1. And then here we have m equals 1. What do the arrows look like there?
They just go on the line.
They're just on the line, right? Because this line is already slope 1. So if you are on this line, you never actually leave it. Now that's not an equilibrium solution. Equilibrium means this value doesn't change, the output value, the dependent variable. But it's kind of like that. It's kind of an equilibrium solution. Once you're on it, at least we know your trajectory. Here's a better way to say it. It's a straight line trajectory. And it's the only one in the entire plane where you travel in a perfect line all the way across. So let's do one more. Let's do 2. And can you just do a couple of these for me? Can you just finish this up? Take a moment, please. Because it's just boring to watch me do it.
do the arrows compare to this line here, that 2 line? Do they go above it or below it? Like that? Above it, because they're steeper, right? And so all these arrows have slope too. So you just make them, that's the key, that's the key. Now I know the direction of the flow. Now going to y equals 3 is probably gonna, it's not gonna work for me. But I am gonna go to -1. That's this dude here. And at that place, ooh, look, at slope -1, they're all completely orthogonal. Orthogonal is just the awesome fancy word for right angle. These have slope -1, and the line itself, the isocline, has slope 1. So it's this beautiful, just perpendicularity all the way across. Well, that just. Cool. And now we understand. If I said to you, let me ask you a question in a different way yet. Suppose that x at 0 equals 2. What is the limit as t goes to infinity of x of t? What is the long-term behavior of the solution if I start here? Take a second. And then let me ask you another, or what if it's x of t, here's, to compare that to x at time 0 is 0. If you've already worked way ahead in this material, solve that differential equation using integrating factors. Oh, okay, good.
I'm confused, so the arrows are called the isoclines?
So wait, say that again, ask that question again.
Well, the question is just like, how do we know which direction the arrows are going in?
They are, so I set the slope for the direction of the arrow. So for example, when the arrows are at a -1 slope, in other words, down and to the right,
Yeah,
I replace dy dx with -1.
yeah.
And then, so look at that last thing. So where does a -1 slope pop out? Anytime y minus x is -1.
Oh, I see.
You
So
see
it's-
now?
okay,
Yeah,
okay,
good, I'm glad
okay.
you asked. Awesome. Is this, what is this? Is this Pokemon?
Yeah.
Okay, yeah. Good, we good here, Joe? Let's see. Yeah, let's look at GN flow.
Just
Mm-hmm. Yeah, beauty. Yeah, nice. Nice. We get over here, friends. Where's that point on the plane? So that's t equals 0, x equals 2. So, yeah. Yes. Yes.
So below it.
There you go. Yeah. There you go. Minus infinity. Yeah, exactly.
So is that's the sort of domain?
I would just say it's the long-term behavior. So if x at 0 is 2, I'm here, and I immediately rocket up at a velocity of, if x is in meters and t is in seconds, then immediately I have 2 meters per second as my velocity, and that means x is increasing, so I go up, and then it just gets faster and faster, and I just rocket up. So the long-term behavior here is infinity, positive infinity. That's the best we could say. Just x keeps increasing without bound. That's what that means. If I start at 0, my immediate velocity is 0, but that velocity changes the minute I move off of here and becomes negative velocity. So this rockets me down to minus infinity. Kind of cool that we can answer these questions with literally no computer around, right? I think this is just crazy. You look at this, probably before you came in here, this would have just been an utter bafflement. Now you own this. You completely own this. Next week, we will learn a way to get an explicit solution for this thing. So we'll be able to write a formula, y of x equals, blah, whatever that's gonna be. And then we'll own it that way. But for right now, we understand this. I'd like to show you the tool that you're going to want to use for those first 2 problems on the homework, and just you're probably going to want to play with. I've been playing with this tool for just at least a decade. Oh, son of a, what just happened here? Haha, okay. Okay, that looks bad. Looks like we got the wrong input. Let's see what happens. Well, I had it, didn't I? There we are. Beautiful. Boy, would you do me a favor and just down the front lights a little, please? Thank you. Beautiful. So, this tool that is linked to in the content area is a direction field plotter, but it also produces numerical solutions. And we're going to get into how the curves are generated. It's really a method just similar to like how we're doing them. We're following these curves, but there's varying methods. So right here, this is the method we're using to get the curves I'm about to get. This RK stands for Runge-Kutta. This is Runge-Kutta 4. There's all these different methods called Runge-Kutta methods. They're a suite of methods for following the curves in just more sophisticated ways. But that's irrelevant to us today because all I want to do is figure out some solution curves. So look at, we got it right. And all you have to do is click on here anywhere you want and look at that. Not only does it do positive time, but it moved me backwards through time as well. Lou?
Is it just like my view, or is there a reason why the right side curves down quicker than the left? Is it just like what it does?
It's kind of, yeah, I guess, yeah, that's a good question. Let me think about that outside of class. I don't know if I have a better answer for you than it just does. Not super satisfying, but yeah. But there's actually, yeah, and also, Lou, I would say we're only seeing a very small portion of the plane here. X or Y goes from 0 to 3, and X goes from what? I don't know, -4 to 4 or something like that. So it's a little tiny window. But anywhere I click on here, I'm going to get trajectories. Check out that word, trajectories. I can fill the plane with all the beautifully colored possible behaviors. And if I can get really slick and get right on that line, damn, there's that line. That's the only straight line in the whole plane, straight line solution. So that's just, I find that beautiful. So now, for your first 2 problems, and any problem where it's just not, in general, you would never do this by hand. You would come here and do this. But we can sure have some fun now because watch what I can do. Let me clear all curves. So you go to initial points. I'll show you a little how to use this. go to initial points and clear all curves. If you want a very precise solution, you just enter the coordinates of the initial conditions here. So let's say I want the one that goes through -2, good lord, -2, -5, -1. And then I just hit submit. That will show me that trajectory alone. And I now know actually a curve. I know exactly a point that's on it as opposed to my crazy, I guess I typed -2 there. What's that checkbox say? Let's see. Well, that's a lie.
I think it just takes the line.
Yeah, this thing here though, it says if checked phase plane curves, this is the phase plane, phase just means state. Phase plane curves and their associated time plots only show results for positive time. It just seems like a lie. 'Cause it's, anyway, whatever, who cares? Wait, I'm gonna uncheck that box and see what happens. Clear all curves. Okay. Whatever. Clear all curves, do it again. Yeah, that feature is clearly bugged. So let's do, let's clear all curves. Let's just do a couple of fun things here. And this is a way to get one's scientific jollies, if one so enjoys. So let's say I want an autonomous, and actually watch this, one other little tweak here. We can set this for different variables. So if you want x and t, you just go here, and then it's now using x as the dependent variable, which is kind of what I want. What would happen if I filled the plane with the arrows that are associated with dx dt equals sine of x? Seems like it would be a periodic thing, right? We've definitely seen, because sine is all wavy. Seems like something wavy should come out of this. So let's hit that. But we see that it actually doesn't. We'll talk about that in a bit. What a strange thing. Let's actually back out a little bit. I think, let's see, how do we set? We go there to set our window. So let's do this from, say, -10, which is like 3 pi, -3 pi, to +3 pi. Oh, look at that beauty. And then let's do this. That we can probably, let's just leave that alone, because we kind of see what's going to happen. I kind of even made it less. Now I'm going to go to -20 here, to +20. And it instantly reacts. But it, oh shit, no, I'm doing the wrong damn one. Oh, sorry, -20 to 20, I was doing it backwards, there we go. Ooh, and let's add more segments. So this is the number of arrows that you have vertically and horizontally. So check out what these solutions look like. Got a whole range of qualities, but the periodicity is vertical as opposed to horizontal, where we have these bands of behavior that just get repeated over and over again. This looks really beautiful right here. I like that a lot. Let me show you something else. Hey, by the way, quick question. Looks like I've got equilibrium solutions in here, right? Do you see those horizontal lines? What do we have? Let's see. So is this one stable or unstable? Stable, right? Because you move toward it. Is this one stable or unstable?
Stable.
Right. What about that one? Unstable. So notice that we've got these different stabilities as we move through the plane here. That's kind of interesting. Depends on where we start. Let's fix this guy real quick. And now I'm going to make it just something that might look more familiar. That looks like a sign. Let me just write up here what just happened, because you might be a little puzzled by by what just occurred. So the first equation I put up here, and I want to show you a quick way to analyze these in the last 10 minutes. So the first equation I wrote up there was dx dt equaled sine of x. Autonomous, because timed, the independent variable, is not even mentioned in the slope description. So this is an autonomous equation. The second one, the one you're seeing right there, was this one. I don't know what only autonomous means, but this is just pure time. It's completely dependent on time. The state actually doesn't matter at all. This is Calc 1, right? This is Calc 1. What function x of t has a derivative of sine of t? See, notice here, and this is something that will throw you off occasionally in this class. The independent variable is the only one mentioned over here. This is Calc 1. I got a bunch of minus cosine curves shifted up and down, and that is precisely what we see here. Look, here's a minus cosine curve right here, right? Cosine's usually flipped version of this. It's got that peak at 0. So here we're seeing minus cosines just shifted up and down. Have fun with that. There's other versions around. Let me get that off here because I want to talk about one last way to understand this weird infinite equilibria with different stability. So let's take a look at how to view this in yet one more way. So we don't need Calc 1. Calc 1 kind of can help us in some ways. All right, let me get the light up here. Cool. So let's take a look at this. I'm going to make a new graph that you haven't seen yet. Yet one more pair of axes that will reveal things to us that we cannot see otherwise. This is going to represent, and this is only for autonomous equations. The horizontal axis represents the dependent variable, and the vertical axis represents the slope, dx dt. And so this only makes sense for autonomous equations. What I'm going to do is get a sense of how does this slope depend upon the state. So let's make a sine graph. Literally, all I have to do is sketch out, y equals sine of x, and think of the y as this over here. So I'm just going to sketch a good old sine curve here. And that goes on forever and ever. And I can label these. This is pi, this is 2 pi, this is minus pi, this is minus 2 pi, and we know that that continues on ad infinitum, both directions. So now look at what's going to happen here. This thing right here is the state. This is the phase line. So phase just means state. And we're going to look at the flow on the phase line. So notice the most salient thing we can grab before we start anything are the equilibrium solutions. At any time I cross that, the derivative is 0. The slope is 0 at these points. So every single crossing is an equilibrium solution. And there are obviously infinitely many of those.
Isn't the slope 0 at the top and the bottom of the thing?
Don't think about the slope of this curve.
Okay.
So what I'm saying here, Voin, is I'm representing things in a whole different way. I'm saying that the slope in that phase, in that flow diagram that we have, I'm just analyzing that dependent upon the x coordinates. So like there's a separate picture over here where I've got my equilibrium solutions. So when x is 0, I've got an equilibrium solution. Let's do this as well. So when x equals 0, sine of x is 0. Sine of 0 is 0, equilibrium. And then at minus pi, I've got an equilibrium solution. This is good. I'm glad you asked that so that I do this. And then at pi, sine of pi is 0. So anytime x is pi, we just stay there forever. And then those bands just go back and forth. So this is going to be my slope field over here. Here I'm just plotting this equation in a new way. Output, this is my slope. And this is my location. Purely the vertical component of my location. In here, the graph is above the axis, so the slope here is positive. dx dt is positive in this realm, in this little region right here. That means x would be increasing. So I put little arrows there. That makes sense because what is sine of pi over 2? Sine of pi over 2 is 1. So I'm giving you a lot of stuff, and there's many moving parts here, and there's actually moving parts we can't see depending on the graph we're looking at. But the phase plane, sine of pi over 2 is 1, so I put slope 1 things all across there. That's right here. So here's where Voin was looking. Sine of pi over 2 is 1. Remember, this is slope on this axis. Solution curve slope. So if x starts in this region, it moves toward pi. If I start here, the slope is negative, right? This graph says the slope at 3 pi over 2 is actually negative 1. So x is decreasing. And we can see that here. If I did the 3 pi over 2 line, we'd see this. But I don't have to draw all that because here I have this nice analysis just of the flow. Is this a stable or unstable equilibrium at pi?
Stable.
Stable. If you move to the right, you flow backwards. If you move to the left, you flow to the right. So here we have a stable equilibrium. Let's finish this up. Here, the slope is negative between 0 and pi. These are both equilibria. And the slope is negative in here. There's an unstable equilibrium at x equals 0. Stable at x equals pi. And I can see that here. If I went down to minus pi over 2, I would see I have a slope of minus 1 there. Because sine of minus pi over 2 is minus 1. And so my solutions are going to look like this. This is new. I've got bands of equilibria. You always approach and leave equilibria asymptotically. So there's another one up there that I did. And that's what we saw in our direction field, those beautiful leaves forming, pointing to the right. So your problems let you explore this. And you probably can do all of them at this point. It'll take a while, so it'd be great if you had awesome questions for me on Monday. Thank you, friends. Appreciate you. See ya Monday.